Hi guys. Welcome to the next video. Today's video is going to be a grade 12 physics paper. It's going to be the November 2017 paper, and it's the National Senior Certificate, so DBE, Department of Basic Education. I'm just going to jump straight into it. This video is going to consist of question 1 to 5, and the rest of the paper will be in the next video. Okay, cool. So let's have a look. Question 1.1 says the acceleration due to gravity on Earth is greater than that on the moon. So, what does that mean? That means that Earth has got a stronger gravitational force than the moon does. Okay? So, basically, when we are using our gravitational acceleration value, which for Earth is 9.8 meters per second squared, the value on the moon is going to be smaller than it is on Earth. So it's going to be smaller than the 9.8, which we know for Earth. So this question says, which one is correct according to the following statements? So A, the weight of an object on Earth is the same as that on the moon. The mass of an object on Earth is the same as that on the moon. The mass of an object on Earth is greater than that on the moon. And the weight of an object on Earth is less than that on the moon. So remember, mass Mass is the same everywhere. Your mass is your mass. Your mass doesn't change, okay? And your mass is given in kilograms. So if you weigh 65 kilograms on Earth, it means your mass on Earth, the moon, Mars, Jupiter, your mass on all of the planets is going to be 65 kilograms. Your weight, however, weight is equal to mass multiplied by gravitational acceleration. Your weight is dependent on the gravitational acceleration of the planet that you are on. Okay, so if you have a mass of 65 kilograms, to calculate your weight on Earth, we're going to say equals 65 times our Earth gravitational acceleration, which you know is 9.8. 9.8 meters per second squared. So 65 times 9.8 gives us 637 newtons. Okay? So this is if you weighed, this would be your weight. If your mass was 65 kilograms and you were standing on Earth, because Earth's gravitational acceleration is 9.8. Okay? But they're saying to you now that the gravitational pull or force on the moon is smaller or weaker than that of the Earth, which means that your G value on the moon is going to be smaller than 9.8. So let's go and revise the options. It says the weight of an object on Earth is the same as it is on the moon. That is wrong. It is not the same. Your weight will be different on every single planet because every single planet has got a different G value. Okay? Unless you're on a planet that has an identical G value to Earth, that is the only time your weight will be the same on Earth and some other space object or object in space, right? The mass of an object on Earth is the same as that on the moon. Isn't that what I just said? I said that your mass on every planet is the same because your mass is your mass. If you stand on a scale on Earth, on Jupiter, on Mars, the scale will give you the same reading. So this is the correct answer. But I first want to go and I want to eliminate the other ones. So C says the mass of an object on Earth is greater than that on the moon. That's not true. Your mass is the same everywhere. The weight of an object on Earth is less than that on the moon. That's also not true. I just said to you that because the moon has got a weaker gravitational force, it means that your G value for the moon would be smaller than 9.8, which means that your weight on the moon would be smaller than it is on the Earth. So it's definitely not this one. So it means that the answer to 1.1 is B. Okay, the next question says the force diagram below shows the forces acting on a box. So we've got normal force, we've got weight, and we've got a applied force at an angle of theta. So it says which one of the following equations for the magnitude of the normal force, or N, is correct? Okay, so it's very important to remember that if you just had an object with no applied force that was just resting on a surface, it would mean that your normal force would be equal to your weight. Okay? But as soon as you see some force applied at an angle, if this applied force was just straight, as in on the horizontal plane, it would be the same. So it would be normal force is equal to weight, even if you had a horizontal applied force. Okay? However, as soon as you have a force that is being applied at an angle, you immediately need to think red flag. Now we've got something different happening here. Remember, when we have a force applied at an angle, we can't really take that into consideration. So we know we need to split our forces into components. So you know your F applied is going to have an Fx, or otherwise known as F parallel, and an Fy component, or an F perpendicular component, okay? And when you've got a force at an angle, the perpendicular force, or the vertical component of your force at an angle, is now going to implicate your normal force. It's going to have some kind of effect. Because why? Because now weight is not only equal to normal force, weight is equal to normal force plus your vertical component, plus your perpendicular component of the applied force. So now weight is equal to normal force plus Fy. So this is scenario A, where we've got only, this is scenario A where we're only working with forces that happen in one plane. So they're either horizontal or vertical forces. So this is scenario A. Scenario A, normal force is always equal to weight. However, in scenario B, we have got a force that is at an angle, and we now have to take into consideration a vertical and horizontal component. Now it changes. Now our weight is equal to normal force plus our vertical component. So in order for us to figure out what normal force is, we need to make normal force the subject of the equation. So normal force is equal to weight minus Fy. Okay? But Fy is not an acceptable format for this question. So we need to say, well, we need to put Fy into terms of theta. Okay? And we do that by doing this. We say these are my components. This is my Fy. This is my Fx. This is my applied force. And we create our little triangle, our 90-degree triangle. This is our theta. So we are looking for Fy. So this is theta. Okay. This is F. And this is Fy. So this is opposite. This is hypotenuse. So sine theta is equal to opposite, which is Fy, over F. We rearrange to make Fy the subject of the formula. Times F. So sine y is equal to sine theta times f. And now we substitute in what we've put in as fy as what we've calculated here. And our answer becomes normal force is equal to weight minus sine theta times f. And which answer does this 1.2 question correspond to? What does this answer correspond to? It corresponds to answer D. Okay, so you need to be very careful when you've got a force that is coming in at an angle because it changes what normal force will be equal to. Scenario A, we have no forces at an angle. Scenario B, we do have a force at an angle. We need to calculate what the vertical component is in terms of F and theta, so that we can now say normal force is equal to weight minus Fy, or in other words, F multiplied by sine theta. Okay, moving on. So 1.3, a stone is projected vertically upwards from the top of a building at a speed of v meters per second. The position time graph below represents the motion of the stone. Ignore the effects of air resistance. Okay, it says which one of the following combinations below regarding the magnitudes of the stone's velocity and acceleration at time t1 is correct. So time t1, as you can see, is showing you the maximum height of this projected stone. Okay? And one thing that you need to know, an important thing that you need to know when we're dealing with equations of motion, because this is an equations of motion question, is that when an object reaches its maximum height, okay, its velocity is equal to 0 meters per second. Okay? When an object reaches its maximum height, its velocity is equal to 0. So we know the answer that we're looking for has to have 0 in there somewhere. Okay? And we also know that at every point in the movement of this object, at every point in the movement of the stone, unless it is in contact with the surface of the earth, unless it's touching the earth, unless it's hit the ground, its acceleration due to gravity will be 9.8 meters per second squared. So now you're looking for the answer that corresponds with a velocity of 0 and a gravitational acceleration of 9.8. And this is question 1.3. So our answer is A. That's wrong because we don't have, this is correct, but acceleration will always be 9.8 unless the object is in contact with the ground or the earth, okay? Its velocity at its maximum height is 0, so we know that one's wrong. And we also know that this one's wrong. Okay, moving on. 1.4, a trolley of mass m is moving at a constant velocity of v to the right on a frictionless horizontal surface. A ball of clay, also of mass m, dropped vertically, falls onto the trolley at time t, as shown in the diagram below. The ball of clay sticks to the trolley. Which one of the velocity time graphs below correctly represents the velocity of the trolley before and after time t? Okay, so it's important to remember that the first part of the graph will represent the first half of the motion, and the second half of the graph will represent the second half of the motion. Okay, so initially our velocity is going to be v. Our initial velocity for our trolley is going to be v. So it could be this one, it could be this one, it could be this one, or it could be this one. So the only way we're going to tell which answer it is is by figuring out what the value for the second half of the motion is. Okay, we can't eliminate any of them based on the first half of the motion. Okay, then we see that this ball of clay with an additional mass of m falls from the sky and hits the trolley. Okay, so the important thing to remember is that the trolley will not change direction from a ball falling from the top and hitting it. Okay, the only way this trolley changes direction is if it is hit with a force going in the opposite direction, and this force has to have a larger magnitude if it's going to change direction. Okay, it's not coming from the opposite direction, so we know that this trolley is not changing direction. Its direction will stay the same way. So based on that, can we eliminate some of them? We know it's not changing direction. It's going to be moving in the same direction. How do we indicate direction in physics? We indicate direction with positive and negatives. We assign a value. So moving to the right in this scenario will be positive, which means that moving to the left will be negative. And we know that an object falling from above and hitting it is not going to cause it to change direction. So any graph that has got a negative value on the second portion of the graph can be eliminated because we know the object is not changing direction. So that means we can eliminate A because it shows you that it's now changed direction, which it hasn't. And we can eliminate B because it hasn't. It hasn't changed direction. So now we're left with C and D. Okay? And it's important to remember that the velocity of your little trolley is going to decrease. Okay? Remember that if an object is heavier, it's not going to be able to move as quickly as if it were lighter. So now that's the second thing that we can now use to eliminate one of the graphs. If they're saying that the velocity of this system increases after the ball of clay comes into contact with the trolley, we know it's wrong. Because increasing mass when a trolley is moving on a horizontal surface will only cause the trolley to move slower. It will not cause it to move faster. Okay? So, C, what happens? We start with a velocity of v, and v decreases. D, we start with a velocity of v, and v increases. So we eliminate D, and our answer is C. So it's 1.4 C. Okay, next question. A person lifts a crate vertically upwards at a constant velocity through a distance h. The person does work x on the crate in time t. The person now lifts the same crate vertically upwards at a constant velocity through the same distance, but in time 2t. Okay, so they're saying that the crate weighs the same, the crate is being moved the same distance, but in scenario 1, I'm moving it in time t, and in scenario 2, I'm moving it in time 2t. So in scenario 1, I'm moving it that same distance faster, and in scenario 2, I'm moving it that same distance slower. Okay, so if we have a look at the formula for work is equal to the force multiplied by the change in x, the change in either vertical displacement or change in horizontal displacement. In this scenario, we're looking at vertical displacement multiplied by cos theta, which is the angle between your force, the direction of your force, and the direction of your displacement. Okay? So, can you see time as a factor anywhere in this formula? No. The only factors affecting work are the magnitude of the force, the magnitude of the displacement, whether it be vertical or horizontal, and the angle between these two factors. So, In other words, it means that lifting this crate the same vertical distance in a longer period of time will not affect the work that was done. Which means that if the work that was done was X for scenario 1, the work that was done for scenario 2 will also be X. Okay? However, if we look at our power formula, power is equal to work done over change in time. Power does depend on time. So if the question had been about power and not about work, increasing the time by 2 would have halved our power, which meant our answer would have been half x. But it doesn't. It's asking about work. And work time does not have an effect on the work done. Which means what? It means that the work done in scenario A is equal to the work done in scenario B. Okay. Next, we move on to 1.6. The wavelengths of light emitted by a distant star appear shorter when observed from Earth. From this, we can conclude that the star is, okay, so number 1, it says that the wavelength appears shorter. Okay, important to remember, wavelength or lambda is inversely proportional to frequency. What does that mean? That means that as wavelength increases, so frequency decreases. And as wavelength decreases, so frequency increases. So if our wavelength is decreasing because it's getting shorter, it means our frequency is increasing. Okay? And here you can see we've got a longer wavelength, which is a smaller or decreasing frequency. And here we've got a shorter wavelength and an increasing frequency. So we've got a shorter wavelength and an increasing frequency, which means, as you can see from the spectrum, that the light is being shifted to the blue side. Okay, and the other thing you need to remember is that so moving towards means there's a blue shift, which means you'll experience a shift to the blue side of the spectrum with a shorter wavelength and an increased frequency. And moving away is a red shift because we have an increasing wavelength with a decreasing frequency, which is a shift to the red side of the spectrum. You can see longer wavelength and decreasing frequency. So let's have a look. It's saying that the wavelength of light emitted by a distant star appears to be shorter when observed from Earth. So we know shorter wavelength means increasing frequency, and increasing frequency and shorter wavelength means moving towards or blue shift. So now we say, from this we can conclude that the star is A, moving towards the Earth and the light is blue shifted. B, moving towards the Earth, the light is red shifted. You already know moving towards is not synonymous with a red shift. So you can just eliminate. Moving away from the earth and the light is redshifted. So this is true, but the light is not redshifted in this case. The light is blue shifted. So we know that's not an option. Moving away from the earth and the light is blue shifted. Moving away is associated with red, not blue. So that means our answer is A. Our wavelength appears shorter. That means it's got an increasing frequency. And a shorter wavelength and an increased frequency is blue shift. And blue shift indicates moving towards. So that means that the star is moving towards the earth and the light is blue shifted. Okay. Then we have a look at the next question, 1.7. It says, two identical light graphite-coated spheres P1 and P2 are suspended using identical thin insulated threads. P1 is charged, but P2 is neutral. The spheres are brought into contact with each other as shown in the diagram, in diagram 1. So you can see in diagram 1, we've got them coming into contact. And thereafter, the spheres assume the positions as shown in diagram 2. So this is one of the formulas that is not on your formula sheet. And the formula goes charge nu is equal to charge 1 plus charge 2 divided by 2. Okay, and this is the formula you use when the question asks or tells you that the spheres or the charged spheres have come into contact and then are separated. And then they ask you, what is the new charge? So they say sphere 1 has a charge of X, sphere 2 has a charge of Y. They come into contact. What is the charge after they've come into contact? So then you say Q nu is equal to X plus Y divided by 2. You need to obviously substitute. If it's a positive charge, it needs to be positive X. If it's a negative charge, it needs to be negative Y. You divide that by 2, and that will give you the new charge. And the new charge will be identical for both spheres. Okay, so let's have a look at the question. It says, which one of the following statements concerning the charges on the spheres possibly explains why the spheres move apart after touching as shown in diagram 2? So diagram 2, can you see that this is representing repulsion? You can see that P1 is repelling P2. They're not attracting one another. So that means that they need to have the same charge. In order for you to have repulsion, you need to have like charges. Like repels, opposites attract. Okay, so this means that P1 and P2 both need to either be positive or they both either need to be negative. Remember that after they've come into contact and you've used this formula, their charges are identical. Okay, so you know the magnitude of the charges on P1 and P2. It's not going to be A and it's not going to be B, because after they've come into contact, they're going to have an identical magnitude of charge. So it's got to be either C or D, because it says that the magnitudes are equal in scenario C or D. Okay, and the other thing we know is they need to have identical charges, because if they have opposite charges, they would be attracting, they wouldn't be repelling. So it can't be C, because positive would attract negative, which means our answer has to be D, because positive would repel a positive, because like charges repel. So the answer to 1.7 is D. Okay, next question, 1.8. When a resistor of resistance R is connected to a battery of EMF E and negligible internal resistance, the power dissipated in the resistor is P. If the resistor is replaced with a resistor of resistance 2R without changing the battery, the power dissipated will be. Okay, well, you now need to go to your formula sheet and you need to look for a formula that includes resistance, power, and EMF. But, okay, EMF, when there is negligible internal resistance, can also be written as V. Okay? Because EMF is only an applicable term when you have internal resistance, because it means that the EMF and the voltage will be different. But in this case, because we have negligible internal resistance, it means that V will be equal to EMF. So you're looking for a formula on your formula sheet that includes resistance, voltage, and power. So let's go. Let's go to our formula sheet and let's see. Here's all your power formulas. You're looking for something that includes power, voltage, and resistance. And bingo, there's your answer. So we go back. And we say, okay, cool. Well, our formula is P is equal to V squared over R. And they say, okay, well, if I change my resistor to a resistor of 2R, so in other words, P is equal to V squared, because everything else will stay the same, over 2R. How will changing my resistance to 2R implicate my power? And you can see from this formula that power is inversely proportional to resistance. Why? Because on this side of the formula, we've got power in the numerator position. And on this side of the formula, we have resistance in the denominator position, which means they're inversely proportional. It means that as power increases, resistance will decrease, or as resistance decreases, so power will increase. Okay? So if I increase my resistance by a factor of 2, it means that my power must decrease by a factor of 2 as well, which means 1.8's answer is B. Okay. Next one, the diagram below shows the current carrying conductor lying in a uniform magnetic field directed to the right. The current flows into the page. So I just want to show you something quickly. You can see here that they've shown you an X on your conductor, and they've told you that the current flows into the page. In another scenario, they won't be so nice. They'll just give you this and they'll expect you to know that the X means that the current is flowing into the page. And the reason for that is because you need to know these. You need to learn these off by heart. If it's an X, it means that current is flowing into the page. If it's a dot, it means that current is flowing out of the page. And when we are dealing with current carrying conductors, we focus on the left-hand rule, Fleming's left-hand rule. So that means you put your hand into this position, you point this finger in the direction of the magnetic field, which is to the right. You point this finger in the direction of the current, which is down towards into the page. And then your thumb will point in the direction of the force. Okay? And your answer, I can't really show this to you right now, obviously, because this is an online session, but the answer is C. If you've done it correctly, the answer to 1.9 is C. Because if you've put your hand in the correct position, this finger should be pointing this way. This finger should be pointing into the page, so towards the page, and this thumb would then be pointing down. So your answer is C. Okay, just remember Fleming's left-hand rule we use for current carrying conductors. There are other scenarios where Fleming's left-hand rule is not appropriate and you actually need to use the right-hand rule. Okay, now we move on to the last question, 1.10. Light of a certain frequency is shone onto a metal M and electrons are ejected from the surface. The same source of light is shone onto another metal N. The electrons ejected from the surface of metal N have a much higher kinetic energy than that of metal M. This means that, okay, well, first things first, your threshold frequency, which we show with these symbols, is the minimum frequency needed for electrons to be ejected from the surface of a metal. Okay? So if the frequency of your light that is being shone onto the surface of the metal is equal to your threshold frequency, it means that electrons will be emitted. Okay? If the frequency of the light that is being shone onto the metal is higher than your threshold frequency, it means that electrons will be emitted and they will have a larger kinetic energy or a higher kinetic energy. So they're saying that the electrons ejected from the surface of metal N have a much higher kinetic energy than that of metal M. So what does that mean? It means if they have a much higher kinetic energy, it means that the metal N has got a lower threshold frequency and metal M has got a higher threshold frequency, because the increase in frequency from the threshold frequency will translate to metal N's electrons having way more kinetic energy. So this means that metal N has the same work function as M? No. Metal N has a larger work function than M? No. C, the threshold frequency of metal N is higher than that of metal M. No, because if metal N had a higher threshold frequency, it would mean that its electrons would not have additional kinetic energy. Remember, the frequency of the light needs to be far above the threshold frequency in order for the kinetic energy to increase. And so the last one says the threshold frequency of metal N is lower than that, and that is correct. Because metal N has got a lower threshold frequency, which means all the additional frequency that exceeds the threshold frequency of metal N is used to increase the kinetic energy of the electrons that are being ejected from the surface of metal N. So your answer to 1.10 is D. Okay, so 1.10 threshold frequency is equal to the minimum frequency needed for electrons to be emitted from the surface of a metal. And if the frequency of your light is above your threshold frequency, it means that your electrons will have more kinetic energy. So your answer is D. Okay, now we move on to question 2. So 2.1, an 8 kilogram block P is being pulled by a constant force F up a rough inclined plane at an angle of 30 degrees to the horizontal at a constant speed. Force F is parallel to the inclined plane as shown in the diagram below. 2.1.1 State Newton's first law in words. Newton's first law says that an object So there is your official definition for Newton's first law. It says Newton's first law states that an object will continue in a state of rest or uniform motion unless it is acted upon by an unbalanced or resultant force. Okay, like I said, you should have a document. The teacher should have provided you with a document that have got all of these official definitions on them. Okay, if she hasn't given it to you, you need to go online and you need to find it. Okay, there'll be a separate one for IEB and CAP students, but you need to learn those formulas off by heart. Sorry, not those formulas, those definitions off by heart, because if they are not extremely close to what is on the memo, you will not get your marks. And it's a very silly thing to lose marks for. Your definition should be where you pick up marks. You shouldn't lose any of those, okay? The next question says 2.1.2, draw a labeled free body diagram for block P. Okay, so you know for free body diagrams, you need to use a ruler. You can't do it freehand like I'm doing it here. Okay, you need to use a ruler and you need to label all of your forces. So here's my object. Okay, we can see that the mark allocation is 4. The mark allocation generally or usually tells us how many forces need to be present on our free body diagram. So we say, okay, well, it's on a surface, so it has to have normal force. Okay, it has a mass or weight, definitely. Like I said, mine doesn't look so great. You definitely have to use a ruler. Okay, it's got an applied force going up the slope. And it has frictional force because it says a rough inclined plane. If it said a smooth surface, it meant no friction. If it says rough, it means there is friction, which means we need friction, and friction always goes in the opposite direction. It says that it's being pulled at a constant force up the rough inclined plane. Okay? So you know friction needs to go in the opposite direction to motion. So this is F applied. This is normal force. This is weight. And this is friction because it's moving in the opposite direction of motion. And that's your free body diagram. Okay? The next question says the kinetic frictional force between the block and the surface of the inclined plane is 20.3 newtons. 2.1.3, calculate the magnitude of force F. Okay, so immediately this is a Newton's question, right? So Newtons we know we're working with. We're going to have to work with F net. So F net is equal to, and now we need to take all of our forces into consideration. Okay, it's moving up the slope, which means up the slope is going to be taken as our positive direction. So we say F net is equal to positive applied force, okay, plus frictional force, which is happening on the same plane, but this is moving in the opposite direction, so minus frictional force. And then we're on an inclined plane, which means we need to take into account the components of weight. This is our vertical components, so WY, or perpendicular, and WX, or W parallel. Okay, so WX also needs to be taken into consideration. The horizontal component of weight is also pulling the object down the slope. So what do we say? It's moving in the opposite direction to which we've taken as positive. So we say minus the horizontal component of weight. And now we go and we sub in, right? So fnet, also you can see here it says that it's moving at a constant speed. Constant speed tells us that fnet is equal to 0. If an object is at rest, as in it's not moving, or if an object is moving at a constant speed, it means that the net force acting on that object is equal to 0. So it means we can say 0 is equal to positive F. They've asked you to calculate positive F. So say positive F minus, they've given you the frictional force, which is 20.37, okay, minus your x component or horizontal component of weight. So that we still need to calculate. So now we go back to our little drawing. Obviously, please remember, you're not allowed to draw components in on your free body diagram. I'm just doing it now because it's easier for me. But if you draw components in on your free body diagram, you will get 0. So you need to draw your free body diagram, and then for the next question, you need to draw another little copy of it that you can use to do your calculations on, okay? Any additional information on your free body diagram and you'll get 0. So we say, so weight X, weight Y. We move one of our arrows. So this is now weight Y. This is weight X. Okay. This is theta. And this is your 90-degree triangle. Okay. So guys, I can't go into depth as to how you do these. It's going to take me way too much time. These are concepts that your teacher should have taught you. So you do need to know how to split things into components, okay? These are just past papers that I'm working through with you. It will take me forever if I have to explain every concept from scratch. But the one thing you do need to know is that the value of your theta, or the angle of your slope, is equal to the angle between your weight and its vertical component. So if they haven't given you a theta for this section and you need it to calculate, for example, like we have to do now, the horizontal component of your weight, you know that the angle between weight and its vertical component, otherwise known as its y component, will be equal to the angle of the slope. So this means that this theta is equal to 30. Okay? So we're looking for Wx, which is opposite. This is W, which is hypotenuse. So that means that sine theta is equal to opposite over hypotenuse. Okay? So sine 30 degrees, because that's my 30 degrees, is equal to my opposite, which was Wx, over W, which is my hypotenuse. Okay, and now we rearrange. We say Wx is equal to sine 30 times weight, but we can calculate weight because they have given us the mass of the block. So the mass of the block is 8 kilograms, and you know your formula. Weight is equal to mass times gravitational acceleration. So it's equal to 8 times 9.8, because that's our value for gravitational acceleration in physics. Okay? And that gives us a weight of 78.4 newtons. Okay? So now we say, okay, well, Wx is equal to sine 30 degrees multiplied by my weight, which is 78.4. And now we solve for Wx. So you say sine 30 multiplied by 78.4 gives us a value of 39.2 newtons. And now we can substitute this answer into this overall equation that we started working with. So minus 39.2. Okay, and now we solve. We say negative 20.37 minus 39.2 gives us a value of 59.57. So 0 is equal to positive f minus 59.57. We can take that over to the other side to make it positive, and F is equal to positive 59.57 newtons. And why does it make sense that it's positive? It makes sense because we chose moving up the slope as positive, which means that it should be a positive value. Okay, so that is the answer for 2.1.3. F is equal to 59.57 newtons. Okay, and now you just have to give me a second to clear this so we've got some space to keep working. Okay, great. Now we can move on to the next question. It says, force F is now removed and the block accelerates down the plane. The kinetic frictional force remains 20.37. Calculate the magnitude of the acceleration of the block. Okay, again, guys, we're working with Newton's first law. So F net is equal to mass times acceleration. Okay, what is my F net going to include if I don't have an applied force pulling everything up the slope and if I just let the block fall? It means that I've got my block, I've got my weight, my x component of weight, and my friction now moving in the opposite direction. Why? Because friction moves in the opposite direction of motion. And they've just told you that the block is released and accelerates down the slope. Okay? So that means that the only force that is causing this block to move down this slope is the horizontal component of weight, and friction now moves to the opposite direction because the block is moving down the slope. Okay? So F net is going to be Wx minus friction. Why? Because it's moving in the opposite direction or the negative direction is equal to mass times acceleration. And now we substitute in, right? You calculate your Wx the exact same way you did in the first scenario. Okay, so that means that Wx is going to be equal to 8 times 9.8 times sine 30 degrees minus, they already said that the frictional force doesn't change, it stays as 20.37, is equal to the mass of the block is 8 kilograms and acceleration is what we're looking for. Okay, so we substitute that in. 8 times 9.8 equals, multiplied by sine 30 gives us 39.2 minus 20.37 equals 8a. So 39.2 minus 20.37 gives us 18.83 equals 8a. We just want a on its own, so we divide this side by 8. We divide this side by 8. And acceleration is equal to 2.35 meters per second squared. Okay, perfect. And that is the answer now to 2.1.4. The acceleration of the block, if it is released and now moves down the slope, is equal to 2.35 meters per second squared. Okay, now again, just give me a sec. Let's have a look at the final question of question 2. 2.2 says, a 200 kilogram rock lies on the surface of a planet. The acceleration due to gravity on the surface of the planet is 6 meters per second. So we already know that this planet is not Earth because its gravitational acceleration is equal to 6 and not 9.8. So the first question says 2.2.1 states Newton's law of universal gravitation in words. So Newton's law of universal gravitation says that so Newton's universal law of gravitation says that each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay, and if we go back and have a look at our formula sheet, it's going to be under forces because it's Newton's law. Our formula is here. Okay, every object or every body in the universe will attract every other body with a force that is directly proportional to the product of their masses, so m1 times m2, and inversely proportional to the square of the distance between their centers. And r is the distance between their centers. G is a constant, which you will find on your formula sheet. G is universal gravitational constant, which is 6.67 times 10 to the negative 11 newtons per meter squared per kilogram to the negative 2. Okay, so it's just 6.67 times 10 to the negative 11. So let's go back. We found our formula now. Let's go see what the question is asking us. Okay, it says a 200 kilogram rock lies on the surface of a planet. The acceleration due to gravity on the surface of the planet is 6 meters per second squared. 2.2.2. Calculate the mass of the planet if its radius is 700 kilometers. Okay? So we say to ourselves, well, we know that our formula is F is equal to our gravitational constant multiplied by m1 times m2 divided by r squared. Okay? Important now, you've got a different gravitational acceleration. So you need to take this into consideration. Okay? There is, in fact, a second formula that would make it much easier. So this is usually when you've got the mass of planet 1 and the mass of planet 2. But there's a second formula that we use during universal gravitation questions. And this is that formula. The gravitational acceleration of a planet is equal to our gravitational constant multiplied by its mass divided by d squared or r squared, the distance between the centers. So that's probably a better formula to use here. You can use the other one, it's just a little bit more time consuming. So I'm going to use the second one that we discussed. G is equal to big G times big M divided by R squared. Okay, so what is our G value in this scenario? It's 6. 6 is equal to, our big G value is what we got off of our formula sheet, 6.67. It's a constant. Remember, the constants are on your formula sheet. It's the first page of your formula sheet. So it's your G constant. Okay, they're asking for the mass of the planet, so big M is what you're looking for, divided by the square of the distance between their centers. And they say that the radius of the planet is 700 kilometers. Okay, so we're just working with one planet at the moment. If this rock is lying on the surface of the Earth or on the surface of that planet, it means that the distance between their centers will be equal to the radius of the planet. But it's important to remember that R needs to be in meters, not in kilometers. Kilometers is not our SI unit or our standard unit. So we say 700 times 10 to the power of 3. Why? Because when I'm converting kilometers to meters, I multiply by 1,000. And 10 to the power of 3 is the same as 1,000. And I square. Okay? And then you plug that into your calculator. And the answer that you get for mass is 4.41 times 10 to the power of 22 kilograms. And that's your answer. That is your answer. 4.41 times 10 to the 22 kilograms is your answer for 2.2.2. Okay. Let's keep moving. Question 3. Okay. Stone A is projected vertically upwards at a speed of 12 meters per second from a height h above the ground. Ignore the effects of air resistance. 3.1. Calculate the time taken for stone A to reach its maximum height. Okay, so we kind of already discussed this. Remember, I spoke to you in the multiple choice section, and I said to you that the velocity of an object when it reaches its maximum height is 0. Okay, and we know that we're working with equations of motion at the moment. So you know that you need to go up to your formula sheet. You need to look for your equations of motion. This is your motion. You see, it's literally called motion. And you need to decide which one of these formulas you're going to use to answer your question. But let's first go down and let's see what information they've given us. Okay, because it's always easier to decide which formula you're going to use when you know what you have to actually substitute into those formulas. Okay, so they say calculate the time taken for stone A to reach its maximum height. Okay, so it says stone A is projected vertically upwards at a speed of 12 meters per second. Okay, cool. So VI, or initial, is equal to 12 meters per second. Okay. Maximum height, we know that V, your final velocity, if we're taking it at the maximum height, is going to be equal to 0 meters per second. Okay. Acceleration is always, so we're taking up as positive here because it's being projected vertically upwards, which means acceleration is negative 9.8 meters per second squared. And they're asking you for time. So each of the motion formulas includes 4 variables. There are 5 motion variables overall. It's VI, VF, AT, so initial velocity, final velocity, acceleration, time, and displacement. But each formula only includes 4 of the 5 variables, which means in order for you to calculate something, you only need 3 variables to calculate the 4. So we have 3 variables. We're looking for time, which is our 4th variable. And if you go to the top, you will see that one of the formulas that includes all of these will be VF is equal to VI plus acceleration times change in time. Okay, so VF is equal to 0, so we say 0 is equal to VI is 12 plus acceleration is negative 9.8 times t. Okay? So the question was, calculate the time taken for stone A to reach its maximum height. You know, the velocity at its maximum height was 0. So the time taken is 1.22 seconds. Okay. Next question. So our answer to this question was 1.22 seconds. Okay. When stone A reaches its maximum height, the speed of stone B is 3v. So I think let's just read the second part here. It says, at the same instant that stone A is projected upwards, stone B is thrown vertically downwards from the same height at an unknown speed v. Refer to the diagram below. When stone A reaches its maximum height, the speed of stone B is 3v. 3.2, calculate the speed v with which stone B is thrown downwards. Okay, so we're looking for speed v. We want to know what is the speed with which stone B was projected downwards. Okay, so now our direction of motion is down. So now our positive direction is down. Remember, I always say take the initial direction of motion as positive. Okay, so for question 1, A was moving up. That was the initial direction of motion, so we take that as positive. And now for question 2, the initial direction of motion is down, so we take down as positive. Okay, so let's make our little summary for 3.2. VI. Okay, it says at the same time that stone A is projected upwards, stone B is thrown vertically downwards from the same height at an unknown speed v. So VI is equal to v. VF. When stone A reaches its maximum height, the speed of stone B is 3v. So let's take VF as 3v. Acceleration is always equal to 9.8. In this case, down is positive, so we don't have to make it negative. We just say 9.8 meters per second squared. Okay? V is what we're calculating, so we need some other parameter. We can't have all of them unknown, right? So what is our time? Let's think carefully. It says at the same instant that stone A is projected upwards. So it's saying when stone A starts its motion, stone B is also starting its motion, okay? And then it says when stone A reaches its maximum height, the speed of stone B is 3v. And you already calculated that it takes stone A 1.22 seconds to reach its maximum height, which means that it takes stone B 1.22 seconds to reach a speed of 3v, because it's saying to us that those two things are happening at the same time. So we say 1.22 seconds. And now we go and we say, okay, well, let's find a formula that incorporates VI, VF, A, and T. So once again, VF is equal to VI plus acceleration times change in T. Now we sub in 3V is equal to, they're both moving in the same direction, so we don't have to substitute in negative and negative or positive and positive. We just say 3V, V plus 9.8 times 1.22. Okay, this goes over, becomes a minus, so it becomes 3V minus V is equal to 9.8 times 1.22, which is 11.956. So therefore 2V is equal to 11.956. Divide by 2 on this side, and what we do on the one side, we do to the other side. So V is equal to 11.956 divided by 2, which gives us a value of 5.978 meters per second. So V is equal to 5.98 meters per second, and this will be my VI, and my VF, which is equal to 3V, is equal to 5.978 multiplied by 3, which is 17.934 meters per second. Okay, so your answer to question 3.2, calculate the speed v with which stone B is thrown downwards. VI is equal to 5.978 meters per second. And that's the answer to that one. Your V for stone B is 5.978 meters per second. Okay, next question. At the instant that stone A passes its initial position on its way down, stone B hits the ground. Calculate height h. Okay, you can see it's only for 3 marks. It's not that hard. Okay. So something that's important to remember is that if we draw out the motion of stone A, they say that stone A is projected up into the air and then it comes back, and it, just read the question quickly. It says, at the instant that stone A passes its initial position on the way down. So we project stone A up into the atmosphere. It reaches its maximum height, H max. And then they say that at the instant it comes back down and is at the same place that it was projected from, okay? It says that at that point, stone B hits the ground. So what is height H? Okay? So something that's important to know is that the motion of a ball that's been projected up into the atmosphere is symmetrical. Okay? So what it looks like on this side will be identical to what it looks like on this side. Okay? Except the only difference is that on this side, we've got our velocity starting at we start with a V max. Our initial velocity is a maximum value because it's projected up into the atmosphere. And our V final is the min because it gets to 0 when it reaches its maximum height. The only difference with side A versus side B is that on this side it starts with a minimum velocity and ends with a maximum. But the amount of time it took to complete this side is identical to the amount of time it took to complete this side. So if this side took 1.22 seconds, then this side will also take 1.22 seconds, okay? The motion of this ball is symmetrical. It's a very important concept, okay? And so if they ask you, what is the total time taken for this ball to complete its entire journey from its starting position to its finish, all you have to do is calculate how much time did it take for it to reach its maximum height, and then you double it. Because whatever it took to reach this height on that side is going to be the same amount of time it takes to move from here to here on the other side. So it took 1.22 seconds for A to move from its initial point to its maximum point, which means it took 1.22 times 2 to go from its initial point back to its initial point on the way down, which is equal to 2.44 seconds. Okay? And they are saying that the same amount of time that it took stone A to come back down to its initial time or its initial position, which was 2.44, is the same amount of time with which it took stone B to reach the ground. So calculating height H is now pretty easy. Now we look at all of stone B's information. We say VI for B, we calculated it. That V value, we calculated it. It was, if you go back to the question, 5.98 or 5.978. Okay? Time, the entire time it took to reach the ground, we've already explained and discussed that it was 2.44 seconds. Okay? Our acceleration is 9.8 meters per second. We're looking at the motion of B, so we can say that it's positive because we'll take down as positive because that's its initial direction of motion. And they're asking us to calculate height, which can also be translated into change in x. So that's what we're looking for. So we have 3 of our 4 values. Now we look for a formula that can help us basically convert these 3 variables into an answer. And the formula that we will be working with is change in x, or in this case, remember, x means horizontal. So we're changing it to change in y because we're actually looking at a vertical distance. We're looking at a vertical change in space. It's not moving from left to right, it's moving from top to bottom. So it's not a change in x, it's a change in y. So change in y is equal to vi times change in t plus half a times change in t squared. And now we substitute in. Vi was 5.978, time was 2.44 seconds plus half times 9.8 times 2.44 squared. Okay? You substitute all of that information in, and you're left with change in y, or height, is equal to 43.74 meters. Okay? 43.74 meters is your answer to 3.3. Okay, perfect. Okay, the last question of question 3.4. Sketch velocity time graphs for the complete motions of stone A and B on the same set of axes. Label your graphs for stone A and B clearly. Okay, so the first thing you have to do to answer this question is you need to choose a direction as positive. Okay, now this one, there's no kind of right one to choose as positive because one of the stones is moving up and one of them is moving down. So it doesn't really matter. So I'm going to go with convention and I'm going to say that up is positive. Okay, so now what do? We draw our axes. We label our axes. Okay, and we also label them to indicate what is going on each. It's a velocity time graph, which means on our x-axis we're putting time in seconds, and on our y-axis we're putting velocity in meters per second. Okay? So they say that they want you to indicate on the graph the time taken for stone A to reach its maximum height and also the velocity with which stone B is thrown downwards. Okay? So we've already calculated. So let's do A first. Okay? A starts with a velocity of 12 meters per second. We don't actually have to indicate it on the graph, but I'm gonna anyway. So this is 12. A starts at 12. And A goes down, and then it reaches 0, which is where it will intercept the x-axis. Okay, it reaches 0 at its maximum height, and then it keeps going. Okay, because remember, A will continue to fall to the ground. So A should be quite a long graph. Okay, and they told you that they wanted you to indicate at what time A reaches its maximum height. So remember, time is on the x-axis. So remember, we calculated our time it would take for it to reach its maximum height as 1.22 seconds. So that is going to be the point at which this graph intercepts the x-axis, because it means at this point our velocity is 0. And it has to be positive here because it's still moving in the upward direction for this first section. For this first section of movement, it's moving in the positive direction. However, as soon as it reaches its maximum height, it changes direction and it starts to move down. And we've taken up as positive. So for the last section of its travel, it is in the negative portion of the y-axis. or the negative quadrant of the y-axis, because it's technically now negative velocities because we've taken up as positive, and once it passes this point, A is moving down. And our velocity moving down will have to have a negative value in front of it. So we substitute this time in as 1.22 because it took 1.22 seconds for A to reach its maximum height. And that was pretty much all they wanted for A. So A is done. But let's go see, what did they want for B? They said that B, they want the velocity with which stone B is thrown downwards. Okay, we took up as positive, which means that B cannot start on the positive side of the y-axis. B moves down, which means it's got to be a negative value. So negative 5.98. And that is where your B graph is going to start. And that's it. That's your graph. Okay. Let's keep moving. Question 4. Question 4 says, a 2 kilogram block is at rest on a smooth, frictionless horizontal table. Okay, what do the words smooth and frictionless? Smooth tells us that it's frictionless, so we don't have to take friction into account here. Okay, it says a bullet of mass 0.15 kilograms traveling east at 400 meters per second strikes the block and passes straight through it with a constant acceleration. Refer to the diagram below. Ignore any loss of mass of the bullet and the block. Okay, so question 4.1 says, state the principle of conservation of linear momentum in words. Okay, so the principle of conservation of linear momentum says that the total linear momentum in an isolated or closed system is constant. Okay, so that's question 4.1. Question now says the block moves eastwards at 0.7 meters per second after the bullet has emerged from it. 4.2. Calculate the magnitude of the velocity of the bullet immediately after it emerges from the block. Okay, so we know we're working with the conservation of linear momentum in this question. And you know that the formula for conservation of linear momentum is the sum of the momentum initially is equal to the sum of momentum finally. Okay? So we now expand on this formula and we say, okay, well, the mass of the bullet, I'm going to say bullet is big B. Bullet. And I'm going to say small b is the block. Okay? So mass of the bullet multiplied by the velocity of the bullet initially plus the mass of the block times the velocity of the block initially is equal to the mass of the bullet multiplied by the velocity of the bullet finally plus the mass of the block times the velocity of the block finally. Okay? So, what is the mass of the bullet? The mass of the bullet is 0.015 kilograms. So, 0.015. The velocity of the bullet initially is traveling east at 400 meters per second. So we sub in 400. Okay. The mass of the block initially is 2 kilograms. And it says that the block initially is resting on a smooth, frictionless surface. So it means plus my 2 kilograms multiplied by, it was at rest, which means its initial velocity is 0. Okay? Is equal to the mass of the bullet afterwards. They said that assume that the mass doesn't change. So 0.015 multiplied by its final velocity. Okay? The final velocity of the bullet is what we're calculating. So we leave that as VF. The velocity of the bullet finally plus the mass of the block, which is 2, multiplied by the velocity of the block at the end. And they say to you that the block moves eastwards at 0.7 meters per second. So we substitute in 0.7 meters per second. Okay, now everything has been substituted in positive, as positive in this scenario, because for the whole scenario, everything is just moving to the right. And so we've just taken to the right as positive. However, if you get a question that requires a change in direction, please be careful. Choose a direction as positive, and then you need to substitute in, if the velocity is now moving in the opposite direction, you need to substitute it in as negative. So just be careful. There could be a more complicated question they could give you, but for now, everything's moving in the same direction, so we can just substitute everything in as positive, okay? You use your calculator. I'm not going to go into, I can say 0.015 multiplied by 400. That gives us 6 plus 2 times 0 is 0 is equal to 0.015 times VBF, otherwise known as velocity of the bullet finally, plus 2 times 0.7, which gives us 1.4. So we take this over. So this becomes 6 minus 1.4 is equal to 0.015 VBF, which means this is equal to 4.6 is equal to 0.015 VBF. We divide by 0.015 on this side. What we do on the right, we must do on the left. So VBF, when you substitute 4.6 divided by 0.015 on your calculator, you should get an answer of 306.67 meters per second. And then let's just check. They asked for the magnitude, so you don't have to say eastwards. If they just ask for the velocity, you need to say 306.67 meters per second eastwards. Okay? But they just said magnitude, so we can just put the magnitude in. Okay, give me a second to get rid of this. Now, it's the last question for question 4 says 4.3. If the bullet takes 0.02 seconds to travel through the block, calculate the length x of the block. Okay, so once again, we're still working with the conservation of linear momentum, okay? But the first thing that comes to mind is that we can use our this length x. It immediately makes me think of the equations of motion. Okay? So, let's have a look. We need to calculate what is change in x, but we can't calculate change in x until we have an acceleration, right? If we're using equations of motion. So let's say VI, VF, A, change in t, and change in x. This is what we're looking for. Okay, VI, what is VI? VI is 400. Remember, now we're working with the bullet now. Okay, because we are looking at the bullet moving through the block. So what is the initial velocity of the bullet? It's 400 meters per second. The final velocity of the bullet is what we just calculated. So it's 306.67 meters per second. The acceleration, this is what we need in order to calculate change in x. So we're calculating A. We're going to have to do a two-step calculation. Okay? We're going to have step 1 to calculate A, and then step 2 to calculate change in x. So in step 1, we're looking for acceleration. Okay? But there's one more variable that we need. Okay? And that variable, it says what? It says that it takes the bullet 0.002 seconds to travel through the block. So now we go to our equations of motion and we say, okay, well, which formula can I use, VI, VF, A, and T, in order to get a value for acceleration? And our formula is VF is equal to VI plus acceleration times change in T. So VF is equal to 306.67 meters per second. Everything's moving in the same direction, so you don't need to say positive and negatives. Everything just stays the same. VI is equal to 400. A is what we're looking for. And T is 0.002. So you rearrange this, you plug it into your calculator, and you get a value of negative 46.67 meters per second squared for acceleration. Why is it negative? It's negative because the bullet is slowing down. If acceleration was positive, it would mean that the bullet is speeding up. Okay, so this was section 1. Now we can use the acceleration that we've just calculated to calculate our change in x. Because if we go have a look at our equations of motion, our change in x formula goes as follows. Vf squared is equal to Vi squared plus 2 times acceleration times change in x. So you can see we needed acceleration to calculate change in x, which is why we started with calculation number 1. This is now calculation number 2. And we just go and we substitute exactly the same way. So we say 306.67 squared is equal to 400 squared, because that was my VI, plus 2 times, and now we substitute in the acceleration that we calculated in the previous question, which, like I said, is a negative. So you need to substitute it in as a negative. 2 times negative 46.67 multiplied by change in x, and that stays change in x because that's what we're trying to calculate. Okay, so you substitute all of this out, you plug it into your calculator, and you get a value for change in x of 0.71 meters. Okay, perfect. So that was the final question there. So the length of this block is 0.71 meters. Okay, and then our last question for today. Okay, question 5. In the diagram below, a 4-kilogram block lying on a rough horizontal surface is connected to a 6-kilogram block by a light, inextensible string passing over a frictionless pulley. Okay, so it's a frictionless pulley, but it says that this block is moving over a rough horizontal surface. And the word rough indicates to us that we are going to have to take friction into consideration. So what do we do? Also, just one more point, it says initially the blocks are held at rest. So question 1 says, state the work energy theorem in words. So what does it say? It says, state the work energy theorem in words. The work energy theorem says that the net or total work done on an object is equal to the change in the object's kinetic energy. Okay, again, this is going to be in a document that your teacher should have given you or that you need to go and find online, and you need to learn your definitions off by heart. Okay, when the blocks are released, the 6-kilogram block falls through a vertical distance of 1.6 meters. Draw a labeled free body diagram for the 6-kilogram block. So you can see, again, we've got it's 2 mark allocation. Usually the mark allocation is an indication of how many forces should be on your free body diagram. Please remember that you really, really do need to draw these with a ruler. Okay? And there's your free body diagram. Why? Because we're doing the 6-kilogram block, and the only forces acting on the 6-kilogram block are tension from the string that it's attached to and weight. Okay? Because weight is pulling it down. Okay? 5.3, calculate the work done by the gravitational force on the 6-kilogram block. Okay? So, what is our formula for work? remember, you need to go back to your formula sheet. I always suggest that you tear the formula sheet off the back of your question paper. Usually the question paper, or this is specifically for CAPS, but usually your formula sheet is at the back of your question paper. Wherever your formula sheet is, whether you're an IEB or a CAPS student, you need to tear that formula sheet off and you need to have it sitting next to you all the time. Okay, it's much easier for your brain to kind of see what's happening and which formulas you should be using if you, number one, make little summaries of all of the variables that you've been given, and number two, have the formulas sitting next to you. Because then your brain can look at the variables that you've listed, it can look at the formulas, and it can say, okay, well, these are the variables I have, and here's the formula that includes all of these variables. So make it easy for yourself. Make it easy for your marker. Okay. Keep your formula sheet next to you. Okay. But we're calculating work at the moment. So we're on 5.3 and the formula for work is work is equal to, we're looking for the work done by weight or gravitational force. So we say work done by weight equals weight multiplied by change in x, but we're not going to say change in x here. We're going to say change in y, because change in x indicates change in x is showing a change in horizontal distance. Okay, change in y indicates a change in vertical distance, and we're working with a vertical distance here. So you say weight multiplied by change in y multiplied by cos theta. Okay, so what is weight? Well, the mass of the object is 6, so we say equals, weight is equal to our mass multiplied by 9.8 multiplied by our change in y, which is 1.6 meters. And then what is the angle between the direction that weight is moving the object in and the direction that the movement is actually happening? Well, weight is acting down. Weight is acting down, but the object is also moving down, because it says when the blocks are released, the 6-kilogram block falls a vertical distance of 1.6 meters, which means that change in y is also happening downwards. So that means that the angle between them, they're parallel. There is no angle between them. The angle between them is 0 degrees. So you say cos 0 degrees equals, so now we say 6 times 9.8 times 1.6 times cos 0. And that gives us an answer of 94.08 joules. And that's your final answer for 5.3. Okay. Okay, our last question for today. As I said, the next video will include questions 6 to, I think there's 11 questions, so 6 to 11. But this first video is only going to include questions 1 to 5. So our final question for today is 5.4, and it says the coefficient of kinetic friction between the 4-kilogram block and the horizontal surface is 0.4. Ignore the effects of air resistance. Use energy principles to calculate the speed of the 6-kilogram block when it falls through a 1.6 meter basically distance while still attached to the 4-kilogram block. Okay, so something very important that you need to know is that if a question says that you need to use energy principles, it means that if you use any other form of calculation, you're going to get it wrong. So you can't use your equations of motion. You can't use anything else. You need to use your work energy principles. Okay? So my strategy here is to just use the most basic kind of format of this principle. And the most basic format for me is work net, or the net work done on an object, is equal to the change in that object's kinetic energy. Okay? And then we expand change in EK, so it becomes work net is equal to okay, so that's the overall formula. And you are allocated a mark here. So it's best that you start with this format of the formula, okay? But we also have a second issue. We need to figure out what is work net. What are all of the work components that need to be considered in this scenario? So work net is equal to what? The work done by gravity, the work done by friction, the work done by normal force. What are we looking at here? So in this scenario, we are in fact looking at the 4 kilogram block, because that's what they've told us. Okay. So what are the forces acting on our 4 kilogram block? So those forces are going to be the work done by friction plus the work done by gravity plus the work done by normal force. Okay? So now we continue and we say, okay, well, work net is equal to what is going to be our formula for our frictional force? Okay, well, frictional force is equal to mu k, your kinetic friction coefficient, multiplied by normal force, multiplied by change in x, multiplied by cos theta. Okay, so that's the work done by friction. Then we say the work done by gravity, which is going to be mass times gravitational acceleration times our change in x, or in this scenario, our change in y, times cos theta, plus the work done by normal force, which is 0. Okay? So now we need to calculate a W net. We need to calculate a value for W net so that we can actually use the other side of the equation. So that's what we're trying to do at the moment. We're trying to calculate what is our W net. Okay, so we did friction. So remember, the only block that has friction is the 4 kilogram block. We did work done by gravity. Okay, so this one's obviously going to be considering the 6 kilogram block because gravity doesn't really play an effect with our 4 kilogram block. And our work done by normal, which is 0. So what do we say now? So now we substitute in. They already gave us the value for friction, which was 0.4. So we can say equals 0.4 which is this is our kinetic coefficient, right? This is the coefficient of kinetic friction, okay, multiplied by our normal force. And for the 4 kilogram block, your normal force is equal to your weight, okay? Because remember in the beginning I explained to you normal force is equal to weight if we have no other forces at an angle. So weight is equal to what? 0.4 multiplied by 4 multiplied by 9.8, okay? Multiplied by our change in x, which if this one moved 1.6 meters, this one also had to move 1.6 meters. So we say times 1.6 times, and then cos theta is going to be the direction between your friction and your basically your change in x, or your change in x. Your change in x is moving from this side to this side, so it's moving this way, and your friction always moves in the opposite direction of motion. So that means that if one is moving this way and the other one is moving this way, that the angle between them is in fact 180 degrees. So we say cos times cos 180 degrees. Plus, now we say we already calculated this one. It was the first calculation that we did. It was calculate the work done by gravitational force. So we just substitute in the value that we calculated there, which was 94.08 plus the 0. Okay, and now you calculate all of that, you add those two up, and you get a work net equal to 68.992 joules. Okay, and now we can substitute this into the first half of our equation, because what are we looking for? We're looking for the speed at which the 6 kilogram block was falling. So we say, okay, well, work net is equal to change in EK, as we've already established at the top here. So we say 68.992, sorry, is equal to half mvf minus vi. Okay, so it's 68.992 is equal to half. The mass that we're focusing on right now is the 4 kilogram block. Okay, and the final velocity of the 4 kilogram block we don't know, minus the initial velocity of the 4 kilogram block was 0, plus now the mass and the velocities of the 6 kilogram block. So we say half 6 multiplied by Vf squared. Remember, their final velocities are in fact going to be identical, okay? Because they're connected by a string. So the speed at which one moves has to be the speed at which the other one moves. Okay, so you could actually even just say 6 plus 4 and do half 10 times Vf squared minus 0. But you substitute all of that away and you get a final velocity of the system, which is equal to 3.71 meters per second. Okay, and that's for question 5.4. Okay, guys, thank you for taking the time, if you've gotten this far, to listen to my video. I hope that some of the things that I've done here have helped, and good luck with your preparation for exams. The second half of the video will be available soon.